The voltage across a capacitor is given by the formula V equals Q over C. And this voltage is directed so that when the capacitor is attached to a resistor, it will discharge the capacitor. For an inductor, voltage is L times di dt. And when it is attached to a resistor, the voltage is such that the current will gradually die out over time. For both inductors and capacitors, attaching them to a resistor will cause some sort of exponential decay in current or voltage or some other property. However, what happens if you attach them to each other? Let's follow along with this diagram. So we start off an inductor and a capacitor attached to each other. In this case, this capacitor is fully charged, but there is no current flowing through the circuit. Now, since this capacitor is charged, there is a voltage across it. Kirchhoff's voltage law says that if there is a voltage across this capacitor, there should be a voltage across this inductor as well. Now, that's not a problem yet, because remember, the voltage across an inductor doesn't depend on current, but on the rate of change in current. So there can be voltage with no current. However, since the voltage does depend on the rate of change of current, having a voltage across this inductor means that there will be current building up. In this next panel, we can see, yes, the capacitor has started to discharge. It started to push some of that current through this wire, and in doing so, it started to build up a current inside this inductor. Now, all this time, the capacitor keeps pushing, so the current gets bigger and bigger and bigger in this inductor, until the capacitor is completely discharged. Now, if the capacitor were attached to a resistor, that would be the end of it. However, the capacitor is attached to an inductor, and the inductor opposes changes in current. So right now, there is a current going through that inductor. And even though it's not being driven by the capacitor anymore, the inductor gives that current a sort of momentum that it will want to keep going, leading to this next panel. The current in the inductor keeps going. Kirchhoff's current law says that it keeps going until it starts charging up the capacitor. Now notice it's charging the capacitor in the opposite direction that it was before. So now the capacitor is opposing this current. So whereas in these cases, the voltage across the capacitor would cause the current to increase, now it's causing the current to decrease, until finally the current has decreased down to zero, meaning this capacitor is now charged up again. But this capacitor is charged up, meaning it has a voltage across it, meaning the inductor will start building up some current, but this time going in the opposite direction. It builds up current as the capacitor discharges until the capacitor is completely discharged, but even though the capacitor is completely discharged, there's current in the inductor. The current in the inductor starts to charge the first side of the capacitor again, and we are right back where we started. This process is very similar to a mass oscillating on a spring. For a mass on a spring, the mass wants to keep going through equilibrium. At the extremes, the spring tries to pull the mass back to equilibrium. Now, if we wanted to look at this from a mathematical perspective, the voltage across the inductor is L di dt, and if you recall, I is dq dt. That means that voltage across the inductor is L d squared q over dt squared. Voltage across the capacitor is q over c. If we apply Kirchhoff's voltage law, we get that those two voltages must add up to zero in a situation like this. If you've taken diff EQ, you will recognize this immediately. If not, don't worry, the answer is sine or cosine. Q of t, and it could be charge, it could be current, it could be voltage. I'm going to use charge as this example. Q of t is equal to Q naught times the cosine of omega naught times t. So Q naught, that represents the amplitude of the charge. In other words, it represents the maximum possible value of charge, such as in this case, the charge on the capacitor. If we were talking about, say, the charge on the current through the inductor, then I naught would be the current through the inductor while the inductor was at maximum current. In any case, this should represent the maximum of whatever value you're looking at. T stands for time, so as time goes by, T gets bigger and bigger. Now this term right here, omega naught, that stands for the angular frequency of the system. Now if you've taken diffie Q, you can also figure out the angular frequency. I'm just going to give it to you. The angular frequency of an LC system, that is the system of an inductor and a capacitor put together, is 1 divided by the square root of L times C. L is the inductance of the inductor, C is the capacitance of the capacitor. Omega is one way to represent how rapidly this oscillation occurs. Omega is very closely related to frequency. We'll get into that in a bit. And more to the point, the period. So in this equation, T represents the period of the oscillation. That is, how long it takes to get from our initial condition all the way through the cycle back to our initial condition. Now, knowing omega, we can say that T is equal to 2 pi over omega. And this is a relationship that you will see very often in oscillating systems. You can take this as true for any oscillating system. All right, so that is a pure LC oscillator. Now, in reality, there's no such thing as a pure LC oscillator. There's no such thing as an inductor capacitor wire that has absolutely zero resistance. And as you can imagine, the resistance will change this somewhat. Most directly, when an inductor and a capacitor is oscillating like this, there is a conservation of energy going on. In this first state, all of the energy is stored in the capacitor. Remember, energy of a capacitor is 1/2 Q squared over C. In this state, all of the energy is stored in the inductor. The energy of an inductor is 1/2 Li squared. But even in, say, this state right here, the capacitor of the inductor plus the capacity of the capacitor, or the energy of the inductor plus the energy of the capacitor adds up to some constant value. The energy trades back and forth between the inductor and capacitor, but it always remains the same. However, once we put in a resistor, that changes. So how do we describe what's going on with a resistor? Well, I would have to add an additional term right here, plus R dq dt, because current is dq dt. Again, if you've taken diffie Q, you know that makes the problem a lot more complicated. So we're going to look at what's called the underdamped case. And I'll get to why I'm calling it underdamped case in a second. For the underdamped case, the formula for, again, I'm using charge, but you can use any electrical quantity you want, is given by this formula right here. Q naught represents the maximum value at the initial time. This alpha is called the damping coefficient, and it's given by this formula right here, R over 2L. R is the resistance of the resistor, L is the inductance of the inductor. And instead of oscillating with this omega naught that we found up here, we oscillate at an angular rate of omega prime, which is given by this formula right here. This does seem like a lot of math, but it's not too terribly difficult, and we'll do a couple of problems on this. Sometimes we like to separate the oscillating component from the decaying component and call it like this. So this is amplitude as a function of time, which is this Q naught e to the negative alpha t. And that is represented by this blue line right here. Whereas the cosine gives it's still oscillating within the bounds of that amplitude. And so for a damped oscillator, you get something like this. You get the red line as a function of time. Now, why am I calling this an underdamped system? Well, consider the formula for omega. Omega is equal to the square root of omega naught squared minus alpha squared. Now consider the formula for alpha. There's no upper limit on alpha. R can be really, really big. R can be megohms, which means that it's quite possible that alpha is bigger than omega naught. And if that's the case, this equation doesn't work. So the scenario is underdamped. The circuit is underdamped as long as this alpha is less than omega naught. In other words, if this resistance is smaller than some critical value. If it's larger, it's either critically damped, in which case this is equal to 0, or it's overdamped, in which case things go crazy. We are not going to look at those cases because they are a lot more mathematically complicated than this situation, and at that point it's not really alternating current.